So for putting each of these in simplified radical form, this is following directly on the heels of what you did yesterday. Remember, you have an option about which method you use to do it. You can use the tree diagram and break it down into its prime factors, or you can look for the biggest perfect square that goes into it. You can even mix the methods, choosing which one might be most convenient on any given problem. For me, I do tend to prefer the biggest perfect square method, and a lot of these work out very nicely for that. So that's what I'm going to be tending to use here. Because as I look at, for instance, the square root of 20, I see that the biggest perfect square that goes into 20 is 4. And so the first thing I would do is I'd write it as the square root of 4 times the square root of 5, which then becomes 2 root 5 for our final answer. In number 2, we have 9 times the square root of 700. Remember, I don't really need to worry about the 9 at the start. All I'm doing is worrying about the square root of 700 at the start and looking for the biggest perfect square that goes into 700. And that's going to be 100 as the biggest perfect square that goes into 700. So I turn it into the square root of 100 times the square root of 7. And that 9, it just continues to hang out front there. All right, so then I take the square roots where I can. The square root of 100, of course, is 10. And so then I do 9 times 10. So that'll give me 90. And then the root 7 does not simplify at all past that, so it just stays 90 root 7. Final answer. Number 3. We got a couple different things going on here. We got the negative on the inside, and then we need to look for the biggest perfect square that goes into 128. That is 64. So I'm going to write this as the square root of 64 times the square root of 2 and times the square root of negative 1 to deal with that negative that was on the inside. And then I can start simplifying the square roots that I can simplify from there. Square root of 64, of course, is 8. The square root of 2 just stays the square root of 2. And the square root of negative 1 is I. And remember, I do like to write the I before the square root. It's better form than leaving it hanging on the end. All right, and then finally for number 4, we got a couple negatives in this case. No, they do not just cancel each other out because one is outside and one is inside. This negative on the outside, it's just hanging out as a number on the outside, just like the 9 was hanging out up here. And so we're just going to be taking our final answer and multiplying it by that negative. So I got that negative from the outside. And then the square root of 15, there's no numbers, there's no perfect squares, other than 1, that go into 15. So I'm just going to leave that as root 15. But I do need to pull out the negative 1 from that 15. And so then you can see that our final simplified radical form here is going to be negative I root 15. Because I do want to again write the I before the radical. The last thing we want to write always when we write in a term is that radical form. That way we aren't having to worry about how far out does that radical go. Is it over the next thing or not? We just make it the last and we don't have to worry about it. So we've seen how to simplify radicals. We've seen how to use imaginary numbers. We're now going to actually utilize those in getting some solutions here. So we're going to be solving these two equations, and we're going to give our answers in simplified exact form, and we'll go ahead and include any imaginary solutions that might come up along the way as well. So for doing this first equation here, x squared minus 50 equals 25, the very first thing we want to do is we want to get the x squared by itself, because there's only one x in the equation. We don't have to factor it or anything here. So then I'm going to start by adding 50 to both sides. And so we then have that x squared is going to equal 75. At this point, we now can get rid of the squared. So that means taking the square root of both sides. Now, when we take the square root of both sides of the equation, what do we need to remember to include? The plus or minus. And so make sure that you remember that as plus or minus 75 there. All right, so now that we are here, we know that x equals plus or minus square root of 75. Can we simplify the square root of 75? Yeah. Yes, we can. And so we're going to now need to go ahead and do that. And so the square root of 75, what's the biggest perfect square that goes into 75? 25, yeah. And so then this is going to become 5 root 3. And notice that plus or minus just hangs out front, which means that we actually have the two separate solutions in. We have that x equals 5 root 3 and x equals the negative 5 root 3. Use the same idea for our second equation over here. Write that one down and go ahead and solve it out. All right, in solving this one again, since the x squared only appears to once, we subtract the 25 from both sides. We have x squared equals a negative 25, which previously would have meant we can do nothing. But now we actually could solve that through. Because when we take the square root of both sides, we're taking the square root of a negative, which remember gives us no real solutions, but although it gives us no real solutions, it does give us imaginary solutions. If I simplify that square root of negative 25, I end up with 5i. So here x equals plus or minus 5i. Or in other words, 5i and negative 5i as our two solutions. And you'll notice in this case that we're told specifically in our instructions up here to give all real and imaginary solutions. If we aren't told to do that specifically, like when you still just see a general question that just says solve, then you would tend to assume that we only need to stick with real solutions. So unless we're told that we do need to include the imaginary solutions, you wouldn't actually go into the imaginary numbers here. We're only doing that because we're told specifically about it. Because imaginary numbers have very specific uses in math, and most of the time, all we care about is real solutions. And so there's like this assumption that when it says to solve, it's really saying find the real solutions. So we have to specify that yes, we're going to go ahead and include the imaginaries on these. All right, we're going to continue with this solving process here. So go ahead and write this one down and go ahead and solve it through. Let's see how well we remember how to solve these ourselves before we jump in and do it together. Now in this case, the x only appears once in our equation, so that's going to tell me that I'm going to try to use the square root principle. So first thing I do, add the 100 to both sides. Now that I have the squared part by itself, this is now where I can go ahead and get rid of the squared. And so we take the square root of both sides at that point. And now we have plus or minus root 80 over here. And yes, I do need to give this in simplified form. So right now, let's go ahead and simplify that square root of 80. So I'm going to go ahead and do it with the biggest perfect square. Again, if you want to make a factor tree for it and circle the pairs, that's perfectly fine. But what is the biggest perfect square that goes into 80? Yeah, 16 is the biggest perfect square that goes into 80. So I'm going to write that as 16 times 5. And then the square root of 16, of course, is 4. The square root of 5 is the square root of 5. And so I go ahead and turn that into plus or minus 4 root 5 equals x plus 3. Well, remember what we did when we were doing these before is because it's plus or minus and I still have to move this 3 over, we'd split it into the two separate equations. And then once I had it in the two separate equations, I could go ahead and I could subtract the 3's from both sides. But this one looks a little bit trickier, doesn't it? Because I now need to do 4 root 5 minus 3. Well, 4 root 5, it of course has a root 5 in it. The 3 does not. These would still be considered to not be like terms because one of them has a square root of 5 in it and the other one doesn't. And so when we go to write that subtraction, like what's that give us when we subtract it, all we can do is write it as 4 root 5 minus 3. There's no other simplifying you can do there. This would be considered the exact form of it. And of course, here we wrote it as two separate answers and two separate equations. You also could write that as one answer where we separate our two solutions with a comma. Same idea there. If you're doing these types of problems on WAMAP, this is what you'd be typing in as your answer there, that sort of thing. Go ahead and do this one on your own as well first, and then we'll come through and we'll do it together here in a few. All right, once we've gotten it to this point where we have the square root part isolated, then we can go ahead and take the square root of both sides. And when we do that in this case, we end up with the square root of negative 9. Yes, we are to include the imaginary solutions here. So we're going to go ahead and now simplify the square root of negative 9, which is 3i. So it's plus or minus 3i. That's why I'm going to go ahead and split it up into the two equations, because I'm going to be operating on it still. So one of them is a positive 3i, the other one's negative 3i. Bringing it back, reminding you, remember, whatever was inside of the square root, notice that part stayed the same. All right, last step. We need to move that 5 over to the other side. Now, how am I going to then do 3i plus 5? Well, are they like terms? No. One of them's got an I in it, the other one doesn't. So all we can do is write it just as 3i plus 5 and negative 3i plus 5. And again, if we were going to just list them both out in one line, we just separate those two with a comma. Right, now having done these, we solved some using square root principle here, but as you might expect, the same kind of rules are going to end up coming up and applying when solving by other methods as well, such as everyone's favorite quadratic formula. And so we can use these same rules about simplifying the radicals when solving something by quadratic formula. To illustrate that, here we're going to pick up with where we were leaving off before when doing quadratic formula, where we've gotten this far with our work, but now we can actually simplify this down further. Before we used to either just stop here or go ahead and calculate it as a decimal. Now I want the simplified exact form of this. So step 1, we're going to need to simplify the square root of 160. Simplify that radical like we always would have before. Before we do it here together, go ahead and write this one down and simplify the square root of 160 on your own first. Now again, I probably would have done the simplifying by using the square root principle, or the biggest perfect square method. But if you did this with the factor tree method, this is what it would look like. Just kind of jog your memory about how that kind of work looks, where we break it all down into the prime factors, then take each of those prime factors, list them out from smallest to largest under the square root, and then circle the pairs. Because remember, if I take the square root of a pair, like the square root of 2 times 2, that just equals whatever the one number was, in this case the 2. And then if you didn't do it that way though, if you did it with the biggest perfect square method, then you would have started by turning it into root 16 times root 10, and the square root of 16 is 4, so it's 4 root 10, which you'll notice is the same thing we get if we just finish doing the multiplication down there. So the square root of 160 becomes 4 root 10. I'm then going to integrate that into the original expression that I had up here. And so it's now negative 6 plus or minus 4 root 10 over 2. And I can now simplify this further. I now need to look and see what I can divide out of every single term on both the top and the bottom. Now notice what I mean by the terms. Terms are separated by addition and subtraction. So negative 6 is a term, 4 root 10 is a term, and 2 is a term there. So all of those are what we're looking at. Now, is there a number that I can divide all 3 of those by? Yep, 2. And so I'm going to then go ahead and divide all of those by 2. So I'm going to do the negative 6 divided by 2. That gives me negative 3. The plus or minus stays a plus or minus. Now I need to do 4 root 10 divided by 2. When you do that, of course, it is going to become 2 times the square root. But is it going to be root 10 or is it going to be root 5? Well, notice that the 2 is not inside of a square root. Since the 2 is not inside of the square root, it cannot affect something that is inside the square root. And so it is going to stay a root 10. And then this is all over 2 divided by 2 is 1. Well, we don't really need to write it all over 1, do we? And so then the whole thing just ends up equaling negative 3 plus or minus 2 root 10. And we're done. That's what we're looking for. This would then be considered the simplified exact form. Obviously, we simplified it by reducing where we could, and it's exact form because we're leaving it with the square root in there. We aren't doing any of the decimals or anything like that that might come along the way. Now the first step, remember, is to simplify the square root of negative 180. And so you're either making a factor tree for that or you're looking for the biggest perfect square that goes into it. Now as you do that kind of work, this might be the sort of thing that you would come up with, but this is not entirely right. And I want you to be able to just see what happens when that does happen. And the reason why it's not entirely right is because the square root of 20 is still not as simplified as it can go. There's still a perfect square that goes into root 20. So you generally kind of want to check after you've simplified and make sure you did in fact find the biggest perfect square. Now, you could go back to the start and redo it, or you could actually continue it from this point. I have this 3i that's hanging out front, but I can now just look to say what's the biggest perfect square that goes into 20. That's 4. And then I could just keep simplifying it from there. And then the last thing we'd do is we'd do 6i root 5, which, yes, is the fully simplified form of the square root of negative 180. And so that's what we're looking to get out of it. But it's just a reminder about if you didn't see what the biggest perfect square was at the start, see that, yes, you can still recover from that and still work through. All right, so now that we've gotten to this point, we again look to see what can we divide out of every single term in order to reduce this. So again, I'm looking at the 12, the 6i root 5, and the 4. Can I divide everything through by 4 here? No. I can only divide everything through by 2, so that's what we're going to do here, is just divide them all by 2. And when we do that, we end up with 6 plus or minus 3i root 5 all over 2. And so then this would be considered our simplified exact form.